And it sort of undid every intuition that I thought I had for this problem. Based on work that occurred earlier by Don Page, and it also, much of it also appeared, some of it, actually wrong things appeared in the paper, not the paper, the book underneath that, Leonard Susskind. So a good deal of what Hayden and Preskill were doing was correcting some misconceptions of mine. So I put my name there, but maybe I should put a goat next to it or something like that. All right, fast scrambling. What is that all about? Supposing we are interested in recovering a bit of information that has fallen into our bathtub, and we're going to recover the information from the evaporating particles that evaporate out of it. Let's forget black holes. Let's talk about particles. They're more accessible. And so we drop in a bit, quantum bit, and it falls into the bathtub. And eventually, of course, the bathtub will be empty because it will evaporate. So sooner or later, that bit has to come out, or at least the principles of quantum mechanics say that bit has to come back out. And the question is, how long does it take? The estimate that I had made, that was based on work of Don Page, was that it would not take longer. In fact, it would not take shorter, I should say, it would not take shorter than the time necessary to emit about half the particles from the bathtub. Strictly speaking, it's probably right to say about the time that it would take to half the entropy to be emitted from the bathtub. And that's a long time, a very long time. Well, of course, it depends on how warm it is out and so forth. But if it's a slow evaporator, which black holes are incidentally, very slow evaporators, that could be an enormous amount of time. Maybe you should imagine covering up the bathtub with a cover and only opening a tiny little hole so that the evaporation products come out very slow. Then it would be more like a black hole. So half the particles come out in an enormous, ferociously long time. And the guess was that information could only be recovered after this extremely long cosmological time. For a stellar mass black hole, that time would be 10 to the 60th years or something ridiculous like that. That was correct within the context of a problem that I had imagined. You create a black hole, and you throw in an extra bit of information, and then you just wait. But Preskill and Hayden, particularly Hayden, designed another experiment, which was something of a shock to me when I saw it. Here was the idea. You first wait for half the particles to evaporate from the bathtub. You have those particles accessible now. You can do experiments on them. You can collect them. You can find out all kinds of things about the bathtub from the evaporation products. But then only after half of it has evaporated do you throw the extra quantum bit in. Then how long does it take the extra quantum bit to come out? The answer has nothing to do with evaporation anymore. It has only to do with the water in the bathtub and how long it takes to scramble that bit among all the water molecules in the bathtub. Time, you could call it. The time that it takes for that bit to equilibrate with I'll try to describe it more fully in a while, but let's just call it the scrambling time. The time that it takes to scramble up what's in the bathtub, nothing to do with the evaporation time. I'll call that scrambling time T star. Now here is a technical way or a diagram that illustrated what they were doing, the technical argument. They said, here comes the bathtub, and time is the bottom, time goes from top to bottom, from bottom to top. Here's the bathtub. Some particles evaporate from the bathtub. Bathtub's a channel. Evaporating particles are a channel. I don't think this needs to be here. S is a scrambler. Scramblers simply means something that makes things thermalized. The only internal dynamics of the system is the scrambler in reality. And after half the particles have been emitted here, an entangled pair of particles or entangled system, one half of it is thrown into the bathtub. Then, after the entangled bits have been thrown in, the system is re-scrambled by its own internal dynamics, and eventually emits a couple of quanta, a couple of bits, a couple of qubits of information. no more than maybe, yeah, questions?
So are you assuming a Hamiltonian scrambler?
We're gonna come to that. We're gonna come to that. Right. That is a very good question. Yes, all right, so a couple of bits are emitted, and then the backdrop is left with 2 or 3 or 4 or 5 more fewer particles than it had after it was scrambled here. Then what Preskill and Hayden showed, which is, to my mind, quite remarkable in itself, is that after that time, C, the entangled qubit over here, is no longer entangled with the bathtub at all, and it is mostly entangled with the evaporation products. It's mixed in among the new evaporation products and the old evaporation products, but there's no memory left of C in the bathtub. To my mind, that was remarkable that they were able to study that, and what they found was that the time scale here was the time to scramble the information in the bathtub. Okay, so let's go on. Let's ask what that means. How scrambled does it have to be for the purposes I just announced? The most scrambled a quantum system can be, we'll see what we mean by scramble as we go along, but the most scrambled it can be is to take a quantum state, an arbitrary quantum state, apply a unitary operation to it. That gives you a resulting random state, where U is chosen completely randomly on the Hilbert space, a completely random unitary operator. Random, technically, with respect to the Haar measure on the Hilbert space of states. The Haar measure is nothing but the measure which is uniform on the unitary group. But Haar scrambling is very, very inefficient. Typically, it takes non-polynomial number of steps. If you try to do the scrambling by a sequence of discrete steps of some kind, it takes a non-polynomial number of steps to do, and would certainly make the time scale for scrambling extremely long. But this is also a very serious overkill. You don't need that much scrambling in order to thoroughly mix a system. So let me define a weaker form of scrambling, which I'll call page scrambling. It may have I don't know the definitions in this subject, so I apologize in particular for people who I insult by not naming the right things after them. I will call this Thorne page scrambling. After the work that Thorne did a good number of years ago, more than 10, almost 15 years ago, here's what page scrambling means. Take a system of n degrees of freedom, n qubits, and scramble it. Divide the system into a subsystem of size m and n minus m. Then the system is page scrambled if the entropy in m is very, very close to the maximal entropy. The maximal entropy would be logarithm of m if for every subsystem smaller than half the size of the whole system, if the entropy is within the maximum to within 1 bit, m over n is typically less than 1, of course, it's less than a half. And so if it's to within less than 1 bit of the maximum entropy in m, for every subsystem less than half the size of the system, then I will say that it's page scrambled. Now, Haar scrambling is far more, what shall I say? It's much harder to do than page scrambling. Haar scrambling, in particular, does imply page scrambling. That's what Page proved, or at least speculates who conjectured, who then proved. But page scrambling does not require anything as thoroughly scrambled as Haar scrambling. We'll talk about what kind of scrambling will do the trick and how long it takes and so forth. But let me just talk about the time scales for the typical time scales for scrambling. Scrambling is diffusion. Typically, it's a diffusion process. It will have n degrees of freedom altogether, n qubits altogether, and you lay them out in a line so that there are only nearest neighbor couplings. Or you put them on a 2-dimensional surface so that there are nearest neighbor couplings on a 2-dimensional lattice, or a 3-dimensional lattice, or whatever the number of the dimensions is. Then the typical time scale for scrambling depends on 2 things. It depends on the dimensionality. That's easy. Why does it depend on the dimensionality? Because the higher the dimensionality, the closer things are to each other. The linear dimension of the system is the number of degrees of freedom to the 1 over d. The reason there's a 2 here is because scrambling is typically a diffusive process, and diffusion takes, stuff grows according to the square of the time. And so for a diffusive process, the time scale for diffusing through the system would grow like the number of degrees of freedom to the 2 divided by the dimensionality. Notice the bigger the dimensionality for a given number of qubits, the faster it is. And also typically depends on the temperature. Beta is the inverse temperature here. The only reason is, yeah.
Oh, 2 questions. One is, when you say typical scrambling time, do you mean page scrambling? Or
I do.
Okay.
I do.
And second question is, I was a little confused. In the hard scrambling, you described the process, right? It's you apply a unitary that's selected at random.
Right.
And in page scrambling, there was no description of a process. You just wrote down.
Well, I'm going to give you an example of a process that does a page scramble. Okay. But I just wanted to just talk about timescales for a minute before we then on processes. Okay. So the typical answer would be the inverse temperature. Why the inverse temperature? Well, the hotter things are, the faster processes take place. The colder they are, the slower things take place. And so it may not be the temperature, but typically some function of the temperature here. The inverse temperature is what I have here. So that's the kind of formula for ordinary systems that you would expect. Notice, as I said, that as d gets bigger and bigger, the time scale gets shorter and shorter. Okay, now there are examples of systems that page scramble in much, much shorter time than that. In fact, I'll show you an example of one which page scrambles in a time of order log n. Now, can I prove that? I can't prove that. I can only read the literature and note it. But I can give you an intuition for why it's true. First of all, consider scramblers that are built the following way. Here are n qubits. Vertical are the qubits. Time runs vertically. And the horizontal connections between them, the pairing of them, grouping them into pairs like this, indicates a random unitary 4x4 matrix of being applied to a pair of qubits. So here, these 2 qubits interact, and these two over here, and so forth. Pick at random which pair is going to interact, and also, to be real safe, let the unitary matrices themselves also be chosen randomly at each step. That's probably overkill. You probably don't need to do that. Then this will page scramble in a time of order n log, not a time, well, yes, a number of operations of order n log n. I'm going to show you a slightly different system. It's the one that Preskill and Hayden actually talked about. I find it a little easier to think about. Instead of just having linear processes, one after another in time, imagine that you have a parallel processing circuit. And the parallel processing means that at an instant of time, any number or some number of interactions can take place more or less simultaneously. Divide the time interval into steps of size beta, and beta will represent the inverse temperature. I'll tell you exactly what it means in a moment. And things can happen simultaneously within a time step. The rule is something like the following. When I say something like the following, I'm going to tell you a rule, which is a definite rule, but I don't think it has to be this rule. I think you can have more flexible rules. But the rule would be randomly divide the qubits into pairs, n over 2 pairs. Having randomly divided them, let those pairs interact. Then go to the next step. Randomly divide them into pairs again, let them interact. Then go to the next step, all simultaneously, with a time scale beta. Right? It's more or less easy to figure out how long it takes for any given bit to scramble with some other bit. After n time steps, after n of these time steps, each time a time step occurs, coincidentally, a time step here roughly means the time scale over which any given bit interacts. It's the time scale such that you can be pretty sure that a given bit is interacting. Every bit interacts once within one time step here. Okay, take the first bit here. How many is it in contact with after the first step? 2 itself and another one. After the next time step, it's in contact, or has effectively been in contact with 4. The new 2 that it interacts with, and the 2 that its partner over here interacted with. So after about n steps, this is not exactly right, but it's approximately correct. I think the actual number 2 is a little bit smaller than 2. But the number of things that a given qubit has interacted with grows exponentially. And that means that the time to communicate between different qubits and to make sure the system is thoroughly interacted is of order logarithm of the number of qubits. Of course, the time scale here is by definition beta, and so it will be beta times the logarithm of the number of steps. Again, the number is n log n, but here we're doing circuitry. The number is n log n for the number of red lines, but we're doing the circuitry in a parallel way, so that means that t star is only logarithm. Now that's really fast when you think about it. You have a large number of degrees of freedom growing like n, and the time scale for really scrambling is only growing log n. So that's quite fast. Yeah.
Is there some kind of precision parameter? Because
I'm sure there is. Okay. I'm sure there is. But this is a colloquium, not a sermon.
What about
So
special
it would have been the
relativity?
same answer if it was the same answer.
What about special relativity then?
Yeah, there is a precision parameter. And it goes in this.
What about special relativity? I mean, how can
What about it?
a particle interact with more than a...
You're jumping way ahead. This is quantum information theory now, not relativity. All right, now a question. Are there Hamiltonian scramblers? The system I described was not a Hamiltonian system. It was a random action of unitary matrices as time went on, as time goes on. Let me at least define it. I believe there are Hamiltonian scramblers, but of course there are Hamiltonian scramblers. Any chaotic system will scramble after a time. Are there fast Hamiltonian scramblers that are as fast as I described on the previous page? So let's first of all just give a very, very rough idea of what it means. Instead of scrambling by a random unitary, we're scrambling by some chaotic Hamiltonian. A chaotic Hamiltonian which has been allowed to evolve for, again, the time of order t star. It again produces some, quote, random state, out of which we can build a density matrix of a subsystem, the subsystem M again, and we can construct the entropy within M. I will call it page thermalized scramble if the entropy in a subsystem here is within the thermal entropy. The thermal entropy means you have to assume that there's an average energy in the problem. So assume that whatever comes out has some average energy. The average energy is partitioned, and M has some average energy. From that average energy, you construct a thermal density matrix, and then there is a thermal entropy. If the subsystems, all subsystems smaller than half the size of the system, have been thoroughly scrambled, meaning that their entropy is within the thermal entropy plus order M over N, then I will call it thermal scrambled or page thermal scrambled. I don't know if anybody has ever done it.
Are you assuming a preferred tensor product decomposition into subsystems here?
Oh.
So when you say any subsystem,
Yeah, no, I understand what you're asking. I don't know the answer.
because obviously if
I don't know
this
the
is a
answer.
pure state,
I don't know the answer, but I think we can come back to it. Yeah. After I discuss the nature of different kinds of Hamiltonians. Yeah. That is it. In fact, we're going to talk about it right now. So the question is, are there fast Hamiltonian scramblers in the sense? Are there fast Hamiltonian? The answer is not by locality. It's not by locality. Are there fast Hamiltonian scramblers? Good. So let me try to define what I mean by a Hamiltonian scrambler. Let's suppose there are a collection of coordinates. And now you can think of these as classical coordinates if you like. They're quantum mechanical, but they might be ordinary bosonic coordinates, positions of particles, or whatever you like. Or they could be qubits, it doesn't matter. And there are n of them altogether. Then I will assume, just as in the case of the qubit problem, that things interact in pairs, I'm going to assume that things interact, the Hamiltonian is constructed of a sum of terms, each of which involves no more than some fixed number of degrees of freedom. For example, 2 degrees of freedom The Hamiltonian can consist of a bunch of paired interactions or a bunch of trilinear interactions, not necessarily trilinear, but can involve 3 degrees of freedom at a time, 4 degrees of freedom at a time. The case I'm going to think about involves 4 degrees of freedom at a time. So the Hamiltonian only involves clusters of fixed size. It's a sum, and it's a sum over different ways of picking the 4 degrees of freedom in this case. I think that should answer the question, because with other ways of decomposing the Hilbert space, this would not be true. Okay? So this is the analog of saying things interact with small number of qubits at a time. The question is, with a Hamiltonian like this, can P star, the star should appear down below, can it be as small as beta log n, where n is the number of degrees of freedom? This is probably something that many of you people might, how many think yes? How many think no? Of course the answer is yes. All right. And now that's not something I knew, but it's something which is closely related to black hole physics. I'm not just going to tell you it's closely related to black hole physics. I'm going to show you a particular Hamiltonian, which I'm quite sure fast scrambles. But the root to it is to think about black holes. Right, so black holes are fast scramblers. Let me take you through the arguments. They're not definitive, but they're very compelling. These are basically the arguments that Hayden and Preskill lifted from me. But I got them wrong. Okay, let's start with a black hole. Here's the black hole horizon. This is basically just flat space. If the black hole is very big, then the region near the horizon just looks like flat space. We can think of it as Rindler space. Rindler space, the outside of the black hole is just this wedge here. There's a Rindler time variable, which runs upward. Blue lines are lines of constant Rindler time. And there's a Rindler space variable, let's call it rho. And there's one particular line here that I will call rho equals rho sub. That should be naught. Sometimes it's rho s, sometimes it's rho naught. The s here actually stands for string, but it's some particular distance, microscopic distance from the horizon, microscopic proper distance from the horizon, where all the interesting thermalization and other things like that take place. You know that according to observers in accelerated reference frame, the region near the horizon is hot. Let's say it has to be hotter than a certain temperature, and that region in there I will call the stretched horizon. It's standard terminology by now. The stretched horizon is a region within rho equals rho s. First definition. Next definition, let's introduce light cone coordinates in this frame. X plus is rho times e to the omega. X minus is minus rho e to the minus omega. These are just flat space coordinates in Rindler space pointing that way and that way. The connection with black holes is the following. The Rindler time, this is called Rindler time, is actually T divided by 4mg for a Schwarzschild black hole, where T is ordinary time as seen from far from the black hole, and 1 over 4mg is basically beta, the inverse temperature. There's some pi's in there that I left out. So omega is inverse temperature times ordinary Schwarzschild time. Those are the things I'll ask you to remember. Can everybody remember that? Good. Okay, here's the puzzle, or here is the Gedanken experiment that caused me a great deal of grief in the past. Supposing Alice, is it Alice who falls into the black hole, or is it Bob?
Alice.
Okay. Alice falls into a black hole with a bit of information with her. Okay. Bob waits on the outside. Presumably, according to the rules of quantum mechanics, somebody on the outside will be able to collect that bit of information, but it will take a certain amount of time for that information to leak out in the Hawking radiation. That time being T star, this mixing time, and the time that Hayden and company are describing when they talk about how long it will take for a bit of information to come out. So, the bit falls in with Alice, and the bit comes out and Bob finds it. Now that's trouble. If information appears in both places, we begin to worry about cloning of information, what I call quantum xeroxing, that if information can be quantum xeroxed or cloned, we have a violation of quantum mechanics. You all know that. I don't have to explain it to you. It's a serious dilemma, but the question is it an observable dilemma? Is there anybody who can see this cloning? If not, we might be inclined to say no real paradox has been exposed with the idea that information can be behind the horizon and in front of the horizon, as long as we can be sure that no observer can ever detect it. So that's the question. Is it possible, in particular, the observer outside can never see anything behind the horizon, but the observer inside, think about that, Bob might jump into the black hole after collecting that bit of information, and now we have two observers behind the horizon who have the same bit. Can we get into trouble? Can Alice communicate with Bob and run into a contradiction with no cloning? All right, so here's the way. It's a subtle argument. It's not a subtle argument. It's a tricky argument. It's not so subtle. It's just that get it upside down and get these inequalities wrong every single time. Okay, so here's the picture. As you can see, the longer that it takes Bob to collect information, the shorter will be the time at which Alice has available to send a message. If Bob waits a very, very long time before jumping in, Alice has to send a message in an extremely short time. The earlier that Bob jumps in, the more time that Alice has to send her message. Now, the problem is, Alice has to send the message in a certain amount of time and has to use a certain amount of energy. How much energy? Roughly speaking, this direction is x minus here. She has that much x minus time to send the message. She has to send it in the form of a quantum with an energy of order 1 over x minus or larger. If the cost in energy is so big that she needs more energy that can fit into the black hole, how much energy can fit into the black hole? Certainly nothing more than the mass of the black hole. So if this time is too small, Alice will have to send her message in a time short by comparison, or use so much energy that she could never have fit into the black hole in the first place. So how much time does Alice have? Well, how much time does she have? She has the time which must be greater than 1 over n. Or in other words, the inverse time here that Alice has must be less than the mass of the black hole. Do I have that inequality right? Yeah, x minus has to be bigger than the inverse mass. The mass of the black hole is the Schwarzschild radius divided by Newton's constant. All right, so this kind of limits what Alice can do. If she has to send the message very quickly, she's out of luck, she doesn't have enough energy. But that, in turn, limits how long Bob has to jump into the black hole if he's going to receive the message. He has to jump in a time, the inequality here is wrong, he has to jump in a time less than r Schwarzschild squared over g. Now the reason I wrote the inequality that way is because I really meant to say is to prevent, not to be able to see Alice's message, but in order to prevent getting Alice's message, x plus has to be larger than this number over here. Where did this come from? This came from using the relation between x plus x minus is rs squared, and saying 1 over x minus has to be less than rs over g. And if you want to avoid paradox, if you want to avoid witnessing cloning, then this time scale here must be bigger than r Schwarzschild squared over g. That bound will be saturated. Oh, we use one more thing. We use that x plus is rho e to the omega. And we imagine that the observer has to be outside this stretched horizon. That leads to a bound, and the bound is that, or the bound is saturated. In other words, saturated that Bob can just barely avoid seeing cloning. If the time scale, the regular time scale, regular time corresponding to this time here, is equal to logarithm of the Schwarzschild radius cube. This is basically the cube of the Planck length. Let's not distinguish rho naught from Planck. This is just basically the Planck length cube here. Or another way of saying it is using the relationship between Schwarzschild time and Rindler time. It says that the time scale for collecting information must not be shorter than beta logarithm of the Schwarzschild radius divided by the Planck length. Everybody get that? If not, I won't go over it again. Okay. That's what the bound says. Now, let's suppose the bound is actually saturated in the most dangerous experiment that we can do. That's the supposition that I failed to make, and it's a supposition that Hayden and Preskill did make, that the bound is fully saturated with the most dangerous possible experiment. Dangerous possible experiment is that it just takes a very short time to collect information. Then the time that it takes to collect information would be minimized by beta logarithm of the size of the black hole.
A question?
Yeah.
I didn't really understand the argument. I'm not asking you to repeat it, but does it absolutely forbid an experiment to detect cloning, or does it just mean that the
statement is
signal will be very weak?
No. Well, I don't know. It will have less than 1 bit, much less than 1 bit. What the argument says is that T star must be bigger than this, or there's a danger, bigger or equal, well, let's say bigger than this, or there's a danger of actually seeing a serious amount of cloning. We can argue whether you can detect a millionth of a bit, and I'm not prepared to argue one way or the other there. Okay, but you're certainly in trouble if the time scale is shorter than that. If the time scale is shorter than that, you're in real trouble. And so that raises the question then, are there any other arguments which tell us how fast information spreads over a horizon? Remember, T star is the time for thorough mixing. Are there any other arguments around which tell us how fast information scrambles over a horizon? Yeah, there are. There's basically classical general relativity supplemented with a tiny bit of quantum mechanics. The same answer will be obtained for charge, mass, temperature. We throw something onto a black hole, we ask how fast does the relevant substance, mass, charge, temperature, how fast does it spread out over the horizon? I'll show you how to calculate it very quickly for charge. Here's the horizon, here's a charged particle falling in. It's falling into the stretched horizon, which is at rho equals rho naught, let's call it. Let's examine it from another point of view. Let's look at edge on. This is the actual mathematical horizon over here. Vertical, meaning falling into the black hole, is vertical. The stretched horizon is a layer above the black hole, this purple layer over here. That's where it's hot. That's where thermalization happens. And these lines, the particle has fallen in, and these lines are the lines of electric field. These are the lines of electric field that presumably terminate on the particle in here. But we're going to count electric charge by just looking at the ends of these lines. Electric charge is the endpoints of electric flux lines. And so if we think that the stretched horizon is the place to study the horizon, then we just want to count the endpoints of flux lines as electric charges. How do these flux lines redistribute themselves over the stretched horizon as the particle goes through? Well, in fact, it's very easy. This is basically flat space. All you have to do is write down the Coulomb field of flat space. This is the Coulomb field for flat space. This is the Z component of the electric field. It's also the rho component. This is the rho component, or a component vertically away from the black hole. Here it is. And then simply substitute in that Z is rho e to the omega, and go to the stretched horizon. Here's what the charge density looks like as a function of Rindler time. The only important thing to note about it, x and y are the coordinates in the horizon. Z is the coordinate perpendicular. The only important thing to note about it is how fast this charge distribution spreads. And it spreads out so that delta x and delta y, spread in x and y charge distribution, grows like rho naught times e to the omega. The spreading is extremely fast, exponential. This is nothing but classical general relativity. And so a charge falling on the horizon of a black hole will spread out with a diffusion diameter, or whatever we want to call it, of rho naught e to the 1 omega. This is omega, not 2 omega. That's a mistake. But then we can ask, how long does it take to cover the whole horizon? The horizon corresponds to a distance of order r Schwarzschild. That's what it is. So when v equals r Schwarzschild, the charge is spread out over the whole horizon, and that takes time omega star. It's log. Again, same log. Log of r Schwarzschild over some microscopic length scale. Converted to Schwarzschild time, that's again beta log r. So those are the real two pieces of evidence. And that's about all there is. Well, there's one more. That says that information, charge, temperature, whatever it is, spreads out over the horizon in a logarithmic time, extremely fast. We can convert this to another statement, incidentally. Beta is inverse temperature. Rs over rho naught is proportional to the square root of the entropy of the black hole. So this is essentially the log of the entropy of the black hole. And I've put the relevant h bar in just here. I suspect there's a bound here. I suspect there's a fundamental bound. I don't know how to even quite define it. But my guess is that there's a bound that says that the derivative of this quantity here with respect to the logarithm of the entropy is always greater than h bar. That's a bound which there is no danger of anything in ordinary physics violating it. Black holes are surely the fastest scramblers in nature. The time to go over the whole horizon is only logarithmic in the size of the horizon. For example, consider a stellar mass black hole with a radius of about 1 kilometer and a temperature of 10 to the minus 8. Really, really cold. Nothing should be going on there. It should be really cold. It is really cold. The scrambling time is only 0.003 seconds to scramble over the entire kilometer horizon. Try to think of anything that scrambles over a kilometer in less than 10 hours. I don't think you can. So black holes, no question in my mind, they are surely the fastest scramblers in nature. Okay, let's come now to the question about Hamiltonian scrambling. Are there scramblers, Hamiltonian scramblers, which scramble that fast, logarithmic in the number of degrees of freedom? Here, string theory shows its power. Why string theory? Because we have quantum mechanical descriptions of black holes. We have quantum mechanical descriptions of black holes in terms of matrix quantum mechanics of a system of d-branes. I'm going to take you through it. You don't have to know anything other than what I tell you about string theory. String theory is a theory of strings, but it's also a theory of objects called d-branes. The only d-branes I'm interested in are d-particles. A d-particle is a particle, and what makes it d, incidentally, d is for Polchinski, and the meaning of d is that strings can end on the d-brane, on the d-particle. So you can have a string connected to the d-particle like so. You can have 2 strings, you can have 3 strings, and so forth. These strings can be created and annihilated. They're like particles. They're localized. They don't move away from the d-brane. They're at the d-brane. But there are creation and annihilation operators for them. Now we can build a field. Not a field in space, but a field in time. Call it X. These are creation and annihilation operators for these strings. The strings also carry a kind of polarization. This is a very rough idea. They kind of point out in some direction. Any one of the 9 directions of space. So this is the creation operator for a string polarized along the A axis. And we just call it X. X super A. It creates a string at the d-brane polarized along the A axis. This is very easy. There's nothing. I'm not going to pull anything very technical out. All right, so A is 1 to 9. Why 1 to 9? Because we're doing 10-dimensional string theory. This is the theory of n-dimensional black holes, basically. So A runs from 1 to 9, and the XAs are these creation and annihilation operators. But the XAs also have another meaning, a completely separate meaning, closely related but separate. They are also the 9 spatial coordinates of the DP brane. That sounds a little bit odd, because the creation and annihilation operators of strings correspond to coordinates of the D brane. What it says is the way you move the particle from one place to another is by creating a little string. So that the coordinate position is nothing but these creation and annihilation operators. The difference between a D brane here and a D brane here can also be thought of as the difference between a D brane with and without a string. So these things are also coordinates. These D0 branes are heavy. They move non-relativistically. Here is the Lagrangian for a non-relativistic particle moving around. And we can either think of it as the Lagrangian for the creation and annihilation operators for the strings, or the Lagrangian for the motion of D branes. Now, what happens if we take a bunch of D branes? If we take a bunch of D branes, they can be connected by many ways by strings. There are many different species of string, the different species each being labeled by 2 D branes, the nth and the nth D brane. So, the creation and annihilation operators are now labeled by 2 indices. Which are the 2 D branes? The kinetic energy operator becomes this, the trace of XA dot, XA dot. And you say, wait a minute. A minute ago you told me that the XAs were going to be coordinate positions. Now you tell me that they're matrices, each one indexed by 2 particles here. Well, let's come back to it in a moment, but let me tell you that there's an interaction Hamiltonian also in string theory for these D branes, and it looks like this. Don't worry too much about what it is, the details of it. And incidentally, all repeated indices are traced over, or summed over. All repeated indices traced over. The trace here is over the MNs, and sums that I haven't written down are over A and B. This is essentially the commutator of XA XB squared. It is the commutator, the matrix commutator, not the quantum mechanical commutator. So this is the interaction Hamiltonian. This term here costs a lot of energy if the different coordinates don't commute. If they do commute, if all the x's do commute, they can be simultaneously diagonalized. If they're simultaneously diagonalized, then the coordinate... Am I doing that? No. If they're simultaneously diagonalizable, then the simultaneous eigenvalues of x become the coordinate positions. If they're not simultaneously diagonalizable, this becomes a horrible non-commutative mess which cannot be described by classical geometry. But, nevertheless, it is the theory of D0 branes. Now notice something about this term in the Hamiltonian. Every one of the 9 n squared matrix elements, classical matrix elements, is coupled to every other one. Here's, for example, a term. This term comes from one of the terms in here. XB, XA, XA, XB, traced over, but I missed it, oh no, it's there, Rn. Right, notice
Should be RM.
Rm is correct, right. Good. Rm is correct. Notice if I pick an XMNB and an XALR, there is always a pair here which can combine to couple these two together. So every pair of matrix elements is coupled to every other pair of matrix elements in terms which have no more than 4 variables in them. This sounds familiar. No more than 4 variables, small clusters, every degree of freedom coupled to every other degree of freedom. It's exactly the kind of Hamiltonian which I speculated about earlier, which might be a fast thermalizer. Well, is it a fast thermalizer? Yes. And to find out, we need to add some energy to these D0 branes and find out what happens to them. Adding energy to them converts them into black holes. A collection of these D0 branes, when excited, become black holes. In fact, they start out as extremely black holes with nasty singularities at their horizon. But when you excite them and give them energy, their horizons become smooth and they become conventional Rindler horizons. This should be ds squared, of course, and of course you will follow the details here. That's the metric of one of these black holes. Here's the Schwarzschild radius, and you can, of course, fill in all the dots here. I'm sure you can, and everybody knows what F is. So I won't bother telling you. And the reason that there's a seventh power here is all obvious. And the dot is just the rest of the metric. But this is just 10-dimensional general relativity, the duality between string theory and general relativity. And from this, we can compute the horizon radius in terms of the temperature and the charge n. The charge n is the number of these zero branes. I should have said, these zero branes are charged objects. They carry their own electric-like charge. So the charge of the object is n. It's also the number of these zero branes. And from that, we can calculate from the temperature of the black hole, from the number of these zero branes, we can easily calculate all the other thermodynamic properties of this black hole. But in particular, we can use the fact that the horizon is rainbow-like to tell us that the time scale for thermalization is just the same Rindler calculation that I did earlier on the blackboard. Not on the blackboard, on the transparency here. That omega star, the Rindler time necessary to thermalize, is just logarithm of the size of the horizon divided by rho naught. In other words, we could have done exactly the same calculation of spreading of charge on this black hole horizon, and we would have found out that this is how long it takes for charge or anything else to spread. So again, one finds the same pattern. The spreading time is logarithmic, but if you convert from RH and rho naught to n and beta, you find out that the time scale to thermalize is beta log n. In the limit of log n is much bigger than log beta. You can drop the log beta term. It's just beta log n. So it seems that these matrix model Hamiltonians must be fast thermalizers. That's not to say we proved that, but the dualities of string theory require that the matrix theory Hamiltonian be a fast scrambler. In fact, it has the correct properties. The individual terms in H involve at most four operators. Every element is directly coupled to every other element, so it has the basic ingredients. But, as usual in string theory, there is no direct proof. There's only circumstantial evidence from these dualities. I can either finish here, well, let's see. We're going to you have some time. A couple minutes?
Yeah, 10 minutes.
Oh, I have 10 minutes. Okay, good. That's enough to scramble. Let me just mention very briefly scrambling in ADS-CFT. Here the situation is a little bit different than what I described, so let me tell you how it works. This is a picture of anti-de Sitter space. If you don't recognize it, I will simply tell you that anti-de Sitter space is a space with a metric that makes every one of these squares have exactly the same size. As we go from layer to layer in coordinate space, each square gets smaller and smaller and smaller. Incidentally, clocks run faster as you'll go to the top. They run faster by the same factor. Clocks here run half as fast as clocks here, run half as fast as clocks here. That's anti-de Sitter space in a nutshell. Here it is. Just put in clocks, it goes slow here, faster here, faster here, faster here. And each one of these cells has a radius which is the radius of curvature of the anti-de Sitter space. Let's imagine that's a big radius of curvature, that we're talking about some fairly big, astronomically big anti-de Sitter space. This is a big radius of curvature. Now, this same theory is known to be describable by a super Yang-Mills theory that lives on the boundary of the anti-de Sitter space. In some sense, it lives on the boundary of the anti-de Sitter space. Each field, such as the gauge field and the matter field, each one has n squared degrees of freedom, where n is the rank of the gauge group. In other words, the gauge fields are themselves matrices. But they're matrix fields. There's a different one at each point. So it's not just n squared degrees of freedom, it's n squared times infinity, where as we move along the horizontal axis, we get new matrix fields at every point. But the way that it actually works is if you cut off the quantum field theory. Cutting off the quantum field theory means introducing a certain cell size horizontally. It is equivalent to cutting off the vertical size, the vertical distance in the vertical direction. Just slice away the top of this and put a cutoff, a lattice field theory, on each one of these cells. That is a perfectly good description of everything that's below it. All the infrared physics below is well described by a cutoff theory in which there are n squared degrees of freedom in each one of these ADS-sized boxes, or each one of these ADS-sized horizontal links here. That's the way the theory works. Another way to say it is that the ADS is described by a lattice of coupled matrix theories. Each matrix theory describes a region whose size is the radius of ADS. So it's a bunch of coupled theories. Why does it look continuous if it's describing regions as big as ADS? Well, it's because, from the coordinate point of view, an ADS-sized region way up near the boundary looks tiny. So it's a coordinate artifact in the sense that we tend to think of a single cutoff length as being small. In fact, a single cutoff length in the field theory is of size RADS. Each cell has n squared degrees of freedom, and they're coupled together as if they were coupled matrix theories. The size of the ADS radius here is g squared, that's the gauge coupling constant, times 10 to the 1/4 times the string length scale. Rho naught is the string length scale in this transparency. All right, that's the setup of ADS. It is just a system of coupled matrix theories. Well, we can now use the Rindler space. Here's a black hole, I'm sorry. Here is the excitation, the thermal excitation of the ADS space. The thermal excitation of the ADS space is nothing but a horizon with a black region underneath. That's it. That's thermally exciting anti-de Sitter space, according to the duality, is just putting a black hole brain, a black brain in, which stretches out over all space. Here's the horizon, and here's the forbidden region down underneath it here. I just draw it as black. So again, it's another black hole problem. Each one of these cells being of size ADS. Now, let's ask how long it takes to thermalize a bit of information that falls onto the ADS over here. I can use the Rindler space calculation, and the same Rindler space calculation, incidentally, the horizons here are Rindler-like. I can use the same Rindler space calculation together with the relationship between the radius of ADS and the n here, and I can find out that a single ADS volume here, one ADS radius volume, is scrambled in time of order t star beta log n. Now, that's not to say the whole thing is scrambled in that time. One cell, which is described by a single matrix theory, coupled to many other matrix theories, of course, is scrambled again in the same time beta log n. So if we imagine the field theory is a bunch of coupled matrix theories, then again we find out that to scramble one n squares worth of degrees of freedom, it takes a time of order beta log n. Let me show you what scrambling would look like. This is just a silly little picture. Here's looking down at the horizon from above. It consists of a bunch of ADS-sized cells. They're all coupled together. Each one has n squared degrees of freedom. Now drop a bit into this cell right over here. One bit localized on a scale much smaller than the ADS radius. ADS radius now we can imagine is big, not maybe on cosmological, but astronomical, and we drop in a single electron. Drop in the electron over here. What does its charge distribution look like? Its charge distribution simply expands very rapidly in a time of order log n. What does that mean in the gauge theory? In the gauge theory, it means we've excited the gauge theory at one point, but just a small number of the gauge degrees of freedom. And then the information spread out over the gauge group, not over space, but over the gauge group, over the n squared degrees of freedom of the gauge group, in a time of order log n. What happens next, of course, is the system begins to behave like in this case, a two-dimensional lattice. To go from here to here to here to here, There we're bounded by the speed of light. And so the system is a sort of composite, not a composite, a hybrid of a system which is local on large scale, but within one cell, it's behaving like an infinite dimensional system. An infinite dimensional system which thermalizes faster than any finite lattice could possibly thermalize. So, it would of course be false to say that string theory proves that there are Hamiltonian fast thermalizers. What string theory proves is that there aren't fast Hamiltonian thermalizers, and string theory is wrong. So all of you will go right up to your offices now and try to prove that there are no Hamiltonian fast scramblers. But you've already told me that you think there are. What does all of this say about black holes? Well, it says something very intriguing. It says there can be no sense in which the horizon of an ordinary black hole, for example, ordinary, forget ABS now, ordinary black hole can be considered to be a two-dimensional collection of pixels interacting locally with each other. There's no sense in which the horizon can be imagined to be filled up with pixels where information propagates from one to the next according to some sort of local Hamiltonian. That would take much too long a time to spread information over the horizon. Every pixel will have to be coupled to every other to create an ultra-fast information scrambler. In a very definite sense, the horizon is infinite dimensional. That's the lesson that we're learning. And a particular example of it is the matrix theories of black holes, which are themselves also infinite dimensional. Good. Thank you.
Wonderful. Comments, questions?
Yeah.
So, one doesn't have to believe in string theory to believe in black holes. So, if string theory weren't true, what would happen to the notion of a black hole being an ultra-fast information?
Nothing.
Is it, in
Nothing.
other words, is it still that?
Yeah. That's how fast charge, temperature, everything else spreads over the horizon.
But you miss this matrix explanation.
The point is, if you are going to look for a quantum mechanical description of the degrees of freedom of a horizon, there will have to be something which is infinite dimensional. Matrix theory is one example. Maybe it's the only example, I don't know. But what it's telling you is exactly this. Quite apart from the existence of matrix theory, just the fact that black hole thermalizes that fast should have been a clue right from the beginning that you can't think of it as interacting local pixels. That they're all going to have to be coupled together. Had I known enough about quantum circuits at one point, and it's in log in that story, I would have read off right from the fact information spreads in a time of order logarithm of n. I would have read off from that that every degree of freedom has to be coupled to every other degree of freedom on the horizon. What the details of a particular model for a particular horizon are, that, of course, string theory provides us some examples. And it provides us examples which do have the right texture, the right feel to them to be able to be fast scramblers. Are they the only ones? Probably not.
I was wondering, like, normally when you have a log function, we say it's slow compared to, say, polynomial. So
The log t is a very small time.
So that was my question. It's fast compared to what?
To t squared, t.
Because it's
Log of
over
t.
the Planck time or something.
Yeah, well, we're going to large. We're thinking about large times. We're thinking about large times. How long does it take you have a zillion degrees of freedom. How long does it take for information to spread? Only a log of a zillion. Whereas you might have expected that it was a zillion squared, one-dimensional, right? Yeah.
What do you think of the following argument, which seems to be part of your argument? If I just take Yang-Mills theory,
Yeah.
cut it in some dimension with some gauge group,
Yeah.
okay, cut it off,
Yeah.
okay, then I can understand it as coming from the matrix model you're describing by compactification.
Yeah.
Right, and therefore, okay, if I believe that that matrix model is the fundamental description, basically what you do when you compactify is you turn off a lot of interactions that otherwise have everybody interacting with everybody, But in principle, if you believe that the fundamental theory is the matrix model,
Yeah.
then you believe that fundamentally all those interactions were in other words, when you compactify down to an SUN in d dimensions,
Yeah.
secretly there are a lot of unexcited interactions between far away degrees of freedom
Far away where? In the
in the
compactification space?
compactification space.
Well, the compactification space is small, typically.
No, but you can
You can, if you don't worry about very high energy excitations, you can pretty much think of it as matrix theory.
That's right.
Yeah.
Right.
Yeah.
So if you think of a cutoff version of Yang-Mills theory
Yeah.
as coming from matrix theory, you already have that every pair is interacting with everybody else. It's just in different compactifications, some interactions are more stronger than other interactions because
Well,
you've
I
expanded around
I
different
think
solutions.
this is best described because I don't quite know what you're saying, and apparently you don't quite know what I'm saying. It will take us some time to
Absolutely.
Right, good. So let's come back to it. You probably do understand what I'm saying. I probably just don't understand what you're saying.
May I risk a question? So, I don't think I know what you're saying. But let me try to phrase it this way, and maybe you can tell me whether I have the gist of it. So you have a property of black holes
Yes.
that is firm, that is the fast scrambling property
Yeah.
of black holes.
Yes.
You're trying to give an explanation or an interpretation of this in terms of horizon dynamics. In terms of a theory that would be...
Well, all I was doing was pointing out that explanations of the entropy and dynamics of black holes that already pre-exist in the literature, string theory ones, have the kind of properties that fast scramblers ought to have. Namely, that they consist of interactions between finite groups of degrees of freedom each term, but that any pair of degrees of freedom can interact. That's the particular character, I think, that characterizes these fast scramblers. Anybody can interact with anybody else somewhere in the Hamiltonian, but the terms in the Hamiltonian only involve some fixed finite number of them. So what I was doing with the matrix theory was just illustrating that here's a theory that's already been proposed for horizon dynamics and so forth that has that kind of property. Yeah, so it has the same kind of property that quantum circuits have if you let every qubit interact with every other one.
So,
You can understand.
Well, you explained.
so I guess the scrambling time is actually, as you said, beta log n.
Yeah.
But beta in this case is the black hole temperature, right? Which is,
Yeah.
or
That's what I'm
one of
taking.
the temperature, which is proportional to the mass.
Right.
So the actual,
Whatever temperature, yeah. Right.
so the actual mixing time is like m log n.
Yes, as viewed from a distance.
Right.
You know what that makes it be like? It's like this n log, it's exactly this n log n. When you're near the horizon and looking at it, you're seeing this parallel processing. When you go far from the horizon, it's all been stretched out into sort of linear processing, one at a time.
Okay, I guess what I was going to
And
suggest.
that's something people knew, that if you look close to the horizon, you see a lot of
Right.
interactions going on simultaneously. Right.
Yeah, okay, so but basically what I was going to suggest is that then, so sure, if you're near the horizon, then it looks like fast scrambling. But if you're far from the horizon, it looks like kind of slow scrambling, actually.
Well, n log n is
But
that slow.
well, it's not that slow. But I mean, in fact, it's kind of limited by the size. The
Yeah.
But it's a causal.
Yeah.
Yeah.
Yeah, it's still faster than n squared. Let's see.
Yeah.
Yeah, so it's
Okay,
still
so
pretty
it's-
fast.
yeah, it's kinda
but just to quantify it, as I said, a stellar mass black hole thermalizes in a time of what, 0.003 seconds, whereas its temperature is 10 to the minus 8 degrees. So I rather suspect. Incidentally, it is of course difficult in nature to make fast scramblers, because if you have to make every degree of freedom interact with every other degree of freedom, you got to send a lot of wires through a small space. So
Right. So actually, this is kind of where I was going, which is that. So I just wonder if you can imagine, forgetting black holes or anything like that, you
Right.
can imagine making a system of length scale m that actually thermalizes in time that's closer, even less than m log m. It's more like m.
Well, that of course, yeah. I don't see any reason why you can't build a Hamiltonian that has a term in it with every degree of freedom,
Well,
or unitary that just
yeah,
does it
forget
one
that.
shot.
Sure, but just say it's a local Hamiltonian interacting
Local,
even
cool.
local, physically local,
Physically
but
local
also
in space.
interacting, small regions.
Right. Yes.
So I mean, I guess I don't know what the answer to that is.
How fast do you want to make it thermalize?
Well, order m rather than m log n, or n the size of the system, basically.
I don't see any reason. I don't see any principal reason. I asked a few people. All the examples that I know are sort of diffusive, and it tends to be n squared. But
Sure.
right.
But if you're in a large number of dimensions, then you
Yeah.
get as fast.
Oh yeah.
Well, but you're still limited by the physical size of the system.
Yeah.
But
No,
I see.
also
No, it's
in an infinite number of dimensions.
Well, Daniel, it's n log n, but it's also beta log n.
yeah, sure.
Right, so,
Yeah.
so if the temperature is the thing which tells you how fast things are going. Right. Right.
So, I'm still trying to struggle with the physical picture. Suppose I have a ball of dust. Presumably, that's not a fast scrambler, but as it collapses to a black hole, all of a sudden it becomes one? Is that really, and if so, what is the physical mechanism that all of a sudden turns it into a fast scrambler?
That's what you might be some kind of non-locality inside the black hole. Like
No, but I don't have a black. I got a ball of dust. I got a star. It collapses. And it's not a fast scrambler, not a fast scrambler, not fast. What does that?
Good question. But you asked the question. You're asking me the question in a way that I don't know the answer.
Can I venture an answer? Because there's a finite correlation length across. I mean, you don't have the type of Hamiltonian where this. So if I have a finite sized dust cloud, this particle of dust does not talk to this particle of dust.
Right.
It's only when they collapse that all degrees of freedom can interact with all of
But
it.
if I'm living on the ball of dust, I don't even know I'm in a black hole. I have no idea. We could be falling through a black hole right now if it was really heavy. Why aren't we fast scrambling?
I have to tell you that I am amazed by this story.
Well, I'm
I'm
surprised.
really puzzled and amazed by it. Information spreading exponentially fast across the horizon is unexpected. On the other hand, it apparently doesn't violate locality because it was all derived from, for example, just the electrodynamics of an ordinary particle falling onto a horizon.
You need a physical mechanism to get you there.
So Lenny, I just want to get a minimalist gist out of it. This is, let's say, 30 years ago. Now, the question is that do you really need quantum feature of black hole? It's just a classical feature, and you are applying.
Well, the only quantum mechanics that I put in was to say that there's this stretched horizon at about a Planck distance from the mathematical horizon. That's the only quantum mechanics that I put
But
in.
you otherwise don't really need quantum.
Not to say that it's a fast scrambler. No.
No, or quantum information. And if you pay with it, I remember it's just statistical mechanics, the difference of systems and stuff like that. The quantum feature is not.
What Page and company realized that I didn't realize, I knew the story about the fast scramblers, although I didn't pay much attention to it until that paper. I knew that story. What I didn't realize is that that's the time scale for re-emitting a bit of information. If you believe in quantum statistical mechanics, if you believe the quantum story, then the connection of this story with Page and Preskill is this becomes the time scale for re-emitting another a bit of information. So there's two fascinating aspects to it. One is that information can be emitted on a very fast time scale. And I'm amazed even by the bathtub. I mean, I thought it just took a long time to evaporate the particles. If you imagine the particles evaporating to a tiny little hole, so that it took 10 years to evaporate a single particle, I would have said it took 10 to the 10 to the 10 to the 10 years to emit a bit of information. Whereas they say, no, it's just a time scale to thermalize the bathtub.
So this is the key ingredient that got us into this kind of thinking, which is classical black hole event horizon.
Well, classical black hole, you don't retrieve information altogether.
Right.
So,
But then if you apply this way of looking at information, then you get it.
yeah. Classical physics would have told you the time that it takes, basically classical thermodynamics and a little bit of, fluid, coarse-grained physics would have told you how long it takes for temperature to spread across the bathtub. You didn't need anything terribly fancy for that. You needed some very fancy things to tell you that that's the time scale to be able to emit a particle. Right? But then the new fancy business here is that this system is behaving like an infinite dimensional system. It's behaving as fast as an infinite dimensional system. What was it? N to the 2 over d. N to the 2 over d is given away to log n.
So that's the kind of statistical mechanical input, is that right?
Well, it's a statistical mechanical and intuition that thermalization is a diffusive process, and so when it happens in dimensions, it takes a time t, which is n to the 1 over d, or n to the 2 over d. Here, it's just logarithm. So it's faster, it's a faster thermalizer than any finite dimensional system of any degrees of freedom.
That's because of the black hole.
The black hole tells you that. The quantum circuit allows it because it allows any bit to interact with any other bit. And the matrix theory allows it because it allows any matrix element to interact with any other one. So there's a collection of ideas there that are all...
But you can throw away all those last three things you mentioned, including string theory. It still stands, right?
yeah, throw away black hole theory, throw away general relativism, throw away...
Okay, let's just take one or two more questions. If anybody has, yes.
So isn't this just the light crossing time? The time is correct.
M log n is the light crossing.
But except for the
N
log
is.
factor. But
Except for the log factor.
so it's just the light crossing time. So all this diffusive business is just assuming that you have a very large box and very small velocity. So it takes a lot of steps. But within one light, if you're moving very fast within one light crossing time, every particle could interact with every other.
Yeah, but then nothing thermalizes like that. And I think is it possible that something could thermalize on such a fast scale? I don't know any causality argument. I just know that most thermalization is diffusive, and so it doesn't work that way at all.
Well, I mean, if you have just a box of perfect gas, every particle just moves with very little scattering. Isn't thermalization just like one crossing time? Or?
I don't know. I don't think so. I don't think so.
Heat travels by the heat placement.
If you have free particles, of course, they just don't thermalize.
Yeah, that's true.
So if the mean free path is very large, then that means you don't.
Yeah, but okay, let's say that you can interact once within one crossing.
But we agree in any case with the n to the 1 over d.
Yeah.
Yeah, the n to the 1 over d is for sure the locality bound. N to the 2 over d is to say that it's diffusive and right. Yeah. So, in my first time I wrote this talk, I wrote n to the 1 over d just to be safe. I decided to take a risk here.
Okay, well, lots of things to talk about. I think he's here for a while, so let's thank him again.